Now with chemistry, everyone, weirdly enough, you'd wonder, why would chemistry become important in medicine? Does anyone have any clues as to why chem is useful in medicine? Tanisha?
To make like drugs and stuff. So like, for example, like diabetes, you'd need I don't know what the drug is, but you need a drug for it to like reduce your
So yeah, so you can
sugars
use
and stuff.
you can use pharmaceuticals. For example, aspirin is acetylsalicylic acid. So it's a weak carboxylic acid, and it can be used to treat platelet disorders. So people who have heart disease, we usually give them lifelong aspirin. So if you know anyone with heart problems, they will be taking aspirin very long term as well. I think the other reason I wanted to mention this is for those of you who might be interested in testing, right? So blood testing, etc. We use a lot of chemistry to do biochemical tests on patients' body samples. So in my fifth year exams, they're in person, they're verbal exams. One of the questions they'll ask me is, how do we measure blood glucose for a patient? And I have to explain spectrophotometry, which is what you're all going to be learning in module 8 with reference to blood glucose. So there's a lot of, I guess, interrelation between chemistry, biology, and physics. So that's kind of the interesting things. Is anyone an avid reader here? No? Okay, there's one book I would really recommend you read. It's called Bad Blood. It's about her name's Elizabeth Holmes. It's a woman who fooled the entire world about blood testing, and she basically proposed that we could test one drop of blood, so do finger prick testing to look at all the other biochemical investigations. And she was about to change the entire medicine field, but it's a really riveting book about how she fooled the entire world. She got to a $4.5 billion net worth.
I heard about that case.
Yeah, you should really read. Sorry, I'm just going to share screen as well. I think it's a must read. I could not put the book down, and I'm not a huge avid reader, but I do like books in general. All right, so we left off at this question. I told you all when we return next lesson, I'm going to teach you this week how to graph disruptions to equilibrium in a concentration time graph. And then we're going to move to the K constant and how to do Rice table. So that will be our goal, our two key goals this lesson. So I think we all identified the stimulus at T1. Just so you can reorient yourself, have a quick read of the question. This is about ammonia and the Haber process. We've written the equation. We spoke about the disturbance at T1. And I told you all there are two phases in a concentration time graph whenever you look at a disturbance to an equilibrium system. What were those two phases, Pranav?
The stimulus phase and the counteraction phase.
Very good. So we're going to look at T2 now. And we're going to try to look at what the stimulus could be. Remember, there are only 3 different stimuli you can have for disrupting an equilibrium system. Only one of the 3. So looking at T2, Gerald, do you want to comment on what you think this disturbance could be out of those 3 factors?
It's probably a change in pressure.
Good. And since pressure, what must have changed as well?
Volume.
Good.
Must have decreased.
Yeah, very good. So we can't really comment on what it is. And typically to change pressure, you would need to change volume. It's quite literally impossible to do so without changing the volume, because then you'd have to increase gas concentrations all equally, for example. Okay. So here it's the pressure volume change. That's your stimulus. And how do you know this, Gerald?
Because the concentration of all chemical species have increased.
Very good. So that's your stimulus phase. Now, let me ask you this. What you might notice is all of them have increased by similar quantity, but that won't always be the case. Is there any relationship between how much each reagent should increase by? And I guess I'll posit this not to Judd, I'll posit to maybe Riasat. The increase in concentration in this initial stimulus phase, is that dependent on anything in particular? Will it be proportional, equal? What do you think? Sorry, you're muted, I think, Riasat. Oh, I just can't hear you. That's all right. We'll go to Mithilesh. Does it have to be equal, Mithilesh, or the increases of these gas concentrations?
No, I think it might have something to do with the stoichiometric ratios.
Okay, so you think it could be to do with the stoichiometric ratio. Okay, and Ansh, what do you think? Does it have to do with the stoichiometric ratio?
Does that have to do with the amount of particles?
Yeah, right. So I want you to remember this. The stimulus phase has nothing to do with LCP and even with the stoichiometric ratio, because remember, the concentrations of all the gases will reestablish based on the stoichiometric ratio in the counteraction phase. We'll talk about that soon, okay? But for now, what you want to remember, it's solely dependent on the initial concentrations. So let me give you another example. Forget these lines. I'm going to draw two lines for you. I'm going to draw one line here, and I'm going to draw another line here. Now, if they said that the volume of this vessel was halved, what you would do is you would find the initial concentration of this substance, let's say it's 1 mole per liter, and say the concentration of this substance is 4 moles per liter. And you would literally double it. Does that make sense? So volume was halved, pressure would double. Do you all agree it had nothing to do with the stoichiometric ratio and it had everything to do with what the initial concentrations of those gases was? So I want you to remember, whenever you're changing pressure in the stimulus phase, the only thing it has to do with is the initial concentrations of those gases. Okay, so this 1 would increase to 2, so it'd go up, spike like this. However, the 4, it would look like it spikes much more, right? And that's simply because the starting concentration was much higher. So that's just a thought that I want you to have in the back of your mind, right? When pressure is a stimulus, the initial change in gas pressures is solely to do with the initial gas concentrations, nothing else. Nothing to do with LCP, nothing to do with the stoichiometric ratio. Good. How about the counteraction phase, though? Have a look at this, everyone. In the counteraction phase, which is this entire phase here, as it's returning to equilibrium, look at how much nitrogen decreases by. Nitrogen drops by that amount. Look at how much your hydrogen increases by. Your hydrogen increases by that amount. And look at how much your ammonia has decreased by. I think what I want you all to notice is, do you all see they're not equal amounts in which they're changing in concentration? Now, who can explain to me what will dictate the proportion as to which each of these gas molecules change by? So Pranav, take it away.
I'm actually not sure about this one.
Okay, right. Make sure you're revising this. I'm going to ask, who do we got? Mahir, any ideas? What is dictating how much these gas moles change by? And this might not be accurate, by the way, but in chemistry, in reality, what will dictate what these gas moles change by?
Is it the concentration?
So remember, the initial concentrations dictated how much all the concentrations would change by in the stimulus phase, but now I'm asking you for the counteraction phase, what do we look at? Because what you'll have to do very soon is you're going to have to start graphing these curves. And if you don't know how much to increase or decrease the gas concentrations by, you will not have a correct graph. So my question is, in this counteraction phase where everything is curving back to return to equilibrium, what is dictating how much the N2, the H2, the NH3 changes by? I'll give you all a hint. Mithilesh mentioned the answer, but for the wrong phase.
Molar ratios?
Yes, very good. So I want you all to remember this. In the counteraction phase, it obeys Le Chatelier's principle, as you all know. That's what the counteraction phase is all about. And the change in concentration will always be in accordance to the stoichiometric ratio. In this case, you'll all see it doesn't necessarily follow that pattern. Your hydrogen should have changed 3 times by whatever the nitrogen changed by, because there is a 1 in front of the nitrogen. But here, since this is just a...
I think you made a mistake. It's actually hydrogen is supposed to be on the less dotted because...
Oh, yes. Apologies. The hydrogen, yes, it's not an H3. Thank you. I was wondering, this graph might have been...
That's what I was thinking.
Good, yeah, so you're right. So the hydrogen is a dotted one. Good. Sorry, all the lines interlapped and I missed the curve. So this is your hydrogen. This is your ammonia. And you've got your nitrogen up here. Very good. Good pickup. So yeah, as you can all see, the hydrogen is changed by the most. Do you all notice that? And if you were to measure it, you would see that the hydrogen changes by 3 parts. The nitrogen is clearly that one. That is your nitrogen. And that should have decreased by 1 part. Again, this graph is not perfect, but the nitrogen should have decreased by 1/3 of whatever the hydrogen decreased by. Okay, and the ammonia would have increased by how many parts, everyone? 2 parts. So that increase in ammonia should have been 2 parts. I'll rub that as well. Good. So that should be your change in ammonia, and that should represent 2 parts of whatever this hydrogen changed by. So that's what I mean when I say that all the change should be accordance with the stoichiometric ratio, especially when you're drawing your concentration time graphs. So that'd be a very, very important principle. So circle it, double it in red. I'd say it's probably the most important thing to do when you're drawing your concentration time graphs. Change in concentration proportional to the stoichiometric ratio. Very good. Now, Rabab, you're going to take it away for the last stimulus at T3. Rabab, what would be the stimulus at T3?
I think it's temperature change.
Why do you say it's temperature? What cues you to temperature?
Because it's not sudden, it's like gradual.
Yeah, very good. First of all, it's very gradual. Do you see a clear stimulus phase, Rabab? So remember, stimulus phase is initially when that stimulus was inputted, there should be a
Yeah.
rapid change in the concentration of substances.
Yeah,
Do you
so
see that here?
there's been a change for the N2, I think, and H2.
Yeah, but as in what I'm trying to say is, do you see in T2 how the gas concentrations sharply changed at that
Oh
point?
no, it's not. It's not like that. It's not rapid.
Yeah. So with T3 or with temperature in general, I want you all to realize you will not see a clear stimulus phase. You will not see any changes in that stimulus phase. And that's because the stimulus was not to do with concentration. It was not to do with pressure volume, so the concentrations do not directly or even indirectly get affected, right? And so they'll only change based on favoring the endothermic or exothermic reaction. So you'll only see that change in the counteraction phase. So no clear change. So that's what tells me that this is temperature as a stimulus. Very good. Good job. So I think you will understand, interpreting these graphs is not hard. If one thing suddenly changes, it's concentration. If all 3 things change, it's pressure volume. And if all of them gradually change, it's temperature. It's that easy. Okay? I guess the most important things are that the change in concentrations in the counteraction phase obeys the stoichiometric ratio. And we're going to test that right now. Okay. Now, this may be a little bit hard because you don't have this image in front of you, and you might have to draw this from scratch. But the one thing I want you all to do, please do not, just freehand draw this. Get a ruler out, and you can generally start with whatever concentrations you'd like. Doesn't have to be the same distance apart. I don't really care about that. But I start with horizontal lines, and I want you to draw what this concentration time graph would look like for the rest of time after the stimulus. Good. So I'll give you about a minute to do that. And while you're doing it, I'll be asking you a couple of questions. So very quickly draw it out. If you'd like, if you have a touchpad, for example, you can screenshot this and annotate it. I'll give you a question. It's from the 2019 HSC. Just make sure you've got a ruler, and generally make hydrogen the highest concentration, H2O in between, CO2 and CO lower. Good. So in 30 seconds, I'm going to ask you to explain it in terms of collision theory, and then we will work on drawing the graph together. Okay, we might start talking about collision theory now. Okay, so I want you to pause the graphs that you were drawing. We'll continue that in a bit. I'm just going to ask you all a couple of questions now. So we'll start with Athava. What are the 3 questions you ask yourself with LCP?
What's the change? Then how does what does the system need to do to partially counteract it? And then which way the reaction goes?
Good. Stimulus opposite direction. So tell me, the stimulus here is CO has been removed. So what's going to happen to everything else?
Yeah. So that means like the system will try to add more CO,
Mm.
and then it'll like partially counteract it. It will favor the reverse reaction, so it can produce more CO.
Good. So you understand it using LCP. Now let's talk about in terms of collision theory. So we'll get Rheosat. I want you to give this a go. You have max 3 lines you can use Rheosat. No more than 3 sentences. I want you to give it a go. Exam answer. How would you answer B?
All right, so okay. Okay. So sorry, I'm just thinking.
That's fine. That's fine.
Decreasing the concentration of CO reduces the frequency of collisions between reactants, which also reduces the number of successful collisions between reactants.
Good.
So since collisions between products don't change, that means the rate of reaction, or the rate of reaction of the forward direction would be less than the rate of reaction for the reverse reaction. It would be less. Since it is less, the reverse direction is favored.
Okay, good. I like your start. In the middle, I want you to work on when you're explaining rate and product and reactants, you don't want to confuse yourself. You don't want to repeat yourself as well, right?
Yeah.
So I guess the way I'd break this down is quite literally your opening line was very good, right? That with decreasing carbon monoxide concentration is going to decrease the total reactant collisions and thus the successful reactant collisions. I think one thing I would mention is the definition of successful collisions. And you can just add on successful collisions where reactant bonds are broken, because that is what defines a successful collision. Okay, so you can write where reactant bonds are broken. Okay, and then you can mention, therefore, there'll be a greater number of successful product collisions relative to successful reactant collisions. Okay, and what is number of collisions over time, everyone? Is that not just rate of reaction? A rate of reaction is defined by the number of reactant collisions divided by a period of time. So if you have a greater number of product collisions over time, you have therefore an increased reverse reaction rate, and you thus shift to the left-hand side, as predicted by LCP. So what I would highlight here, the key things that I'd be looking for if I was examining you and your answers, is that you identify there are less successful reactant collisions. You identified thus there is relatively a greater reverse reaction rate, and thus you link it back to LCP as well. That'd be important. Good. And if it was a 4-mark question, what would you like to do on top of this? Anyone?
Like define the terms.
Yeah, which term? Because you don't have enough lines to define every term. So LCP, collision theory, what are you going to define?
Collision theory.
Yeah, you can give a quick line about collision theory. And Pranav, define it for us.
Collision theory talks about it's a theory of it's a theory which states about how bonds are broken to form like other bonds.
Okay, a bit vague. Gerald, how would you define collision theory?
Collision theory outlines how molecules within a system interact with each other to react.
Again, you guys are basically tipping the iceberg here, right? I want straight to the high yield points. The thing is, a marker I'm looking for is if the student identifies particles have kinetic energy greater than activation energy, and they have correct orientation to successfully break reactant bonds and collisions. That's what collision theory is about. It states that a successful collision where reactant bonds are broken occur under two scenarios. They both need to occur simultaneously. There needs to be energy greater than activation energy, and there needs to be correct orientation. And it's the latter that a lot of students will miss. That is a definition of collision theory. Does that make sense? I don't want an outline. You guys are explaining, it's a theory about particles and bonds. Yes, but what's the key point, right? It explains that a successful collision where reactant bonds are broken occurs when particles collide with sufficient kinetic energy greater than activation energy and correct orientation. Good. Good job. Now let's look at this graph. This is the more high yield aspect. Now, let's look at the stimulus phase. Rabab, will any of the other gas concentrations change in the stimulus phase? Right there. If you draw a vertical line down, I'm asking you, will any of the other gases change at that point in time?
Yes.
I would say none of them would immediately change,
Oh, no,
right? The only thing that immediately changes in that time period T is the carbon monoxide because it was removed at that point in time. Does that make sense to everyone? So I think you all know that as well. Concentration, whenever it's changed, only one of the substances sharply changes its y-axis or concentration value in that time of disturbance. Good. Now, what did I tell you all about the counteraction phase? I said this is the most important thing you can learn today. And what was that, Ansh? Quickly, what was the most important principle you learned about the counteraction phase?
LCP.
Yeah, more specific. Who can tell Ansh what was the most important thing you all got from the counteraction phase?
The change in concentrations is relative to the stoichiometric ratios of each species.
Very good, right? So let's apply that here. What number's in front of carbon monoxide, Mithilesh?
1.
1, right? So what I'm going to do now is we haven't been given y-axis values. I think you all realize that. So we're just going to say this is 0.1, 0.2 for our reference here, 0.3, 0.4. Does that make sense? This is 0.5, 6, 7, 8. Yeah. So each big line here is 0.4, an increase by 0.4, and each small line will just say is 0.1. So Mithilesh, how much did the carbon monoxide change by in the counteraction phase?
Increase of 0.3 moles per liter.
Good. So what you want to all write, what you all want to write now is a change in concentration. So one part in this cooking recipe or chemical reaction represents a change in concentration by 0.3. Does that make sense to everyone? Now we favored our reverse reaction. So your carbon monoxide should increase. What else should increase, everyone? Water. Now you just want to check one thing. Whenever you see water, what's the one thing you'd like to check with this equilibrium system? Because it can be tripping you up here.
If it's a liquid.
Yeah, right. Usually, if it's a liquid, the concentration will immediately just be 1, but they could sometimes try to trick you this way. But this is a gas, so we do include its concentration, right? It will be affected. So water should also increase. And so Gerald, there's a 1 in front of water. So how many units should it increase by?
0.3.
Good. Now, the next thing you want to consider is when did the system return to equilibrium? And you'll agree it's the point where the concentration of carbon monoxide becomes constant in gain. And I could say it's about there. Does everyone agree? About at that point in time, this line is not completely straight, but maybe I'll do it straight for us. Take that out. Yeah, about there. Could say maybe about there, the system has returned to equilibrium. Does everyone agree? At that point in time, the concentration of CO is stabilized. So you want to show that every other gas at that same time point returns to equilibrium. So we'll call this T2. So the key implications here that CO needs to increase by 0.1, 0.2, 0.3. It needs to stabilize right there. So now that I know that, I can just draw a line that plateaus right at that point. Does that make sense to everyone? And you'd obviously continue that line all the way till here.
You increase CO2, not
Oh, apologies. Yes, I've done the wrong line again. Go back. So we have got H2O that needs to have also increased. Good. So we go back to H2O. It needs to go up by 0.1, 0.2, 0.3, and it needs to stabilize right there. So we would draw the graph something like this. Okay, so that's how H2O would look. So what about CO2 and H2? The same things need to happen. Do you all agree they all have a 1 in front of them? What will be the difference though? Pranav, are they going to increase or decrease in concentration?
They're going to decrease.
Yeah, so your CO2 and H2 are going to decrease by 0.1, 0.2, 0.3, 0.1, 0.2, 0.3, and they'll all plateau right there. Right, so you can just draw the lines as such, plateauing perfectly at that point. Good, and if you do this, you have correctly drawn all the changes in concentration. So now do you all see how to apply the counteraction phase, what you learned, that the stoichiometric ratio will dictate the changes in concentration? So the tip here again is find out what one part of changes in the counteraction phase, and then change everything in terms of the number in front of it in the stoichiometric ratio. Since they all had a 1 in front of them, it was an easy question. They all changed by 0.3 units. Okay, if this was a 3 here, it would change by 0.9, for example. Okay, good. And I guess the last thing was they all need to return to equilibrium at the exact same point in time. Okay, good. Maybe I'll just write this in red for all of you. For drawing concentration time graphs for the counteraction phase, the two things I'd want you to all consider is change is proportional to the stoichiometric ratio, and they must return to equilibrium at same time. Those are two things I'm looking out for. Very good. If you guys apply these two things, you will never go wrong with the concentration time graph. It's not hard beyond that. Good. Good job. Shall we all try a question now? Good. Let's move on. Any further questions before I move on? Did that all make sense? Good. So what I've written in red is probably one of the most high yield parts of Mod 5, because concentration time graphs will almost definitely be asked in your HSC and your trial exams. Okay, let's do easier graph. Again, Haber process. So I think you're all realizing how high yield it is just to understand the general kinetics of the Haber process. So the enthalpy change, it's exothermic, and knowing the equation. Forget about A. I think you all know the reason the concentrations does not change between T1 and T2 is to do with equilibrium, right? It's at a dynamic equilibrium. But I want you to explain B. Okay, so with B, I want you to give this a go. So draw it, just doesn't need to be exact, but make sure hydrogen is the highest and nitrogen and ammonia are much lower and closer together. Use ruled lines for the plateaued part. I'm not going to say anything, but I'd like you all to draw this for me and also send a picture in the chat. So once you've done your drawing, take a quick picture and send it in the chat function if you can. Does everyone have Teams on their phone? No, if you don't have Teams on your phone, what you can do is, does everyone have an iPhone? No, that's all right. What you can do is, okay, maybe in the break you can download Teams, and then after the break you can send your picture in, okay, on your phone. Do this as fast as you can. In 30 seconds, I'll start asking people. So this is a past HSC question. It's from the 2005 paper, but it's a very good question. Okay, I guess we'll start our approach to this question. So let's see, who do we have? Let's go with Ansh. What's the first thing you're doing here?
Finding the stimulus.
Pardon?
Find the stimulus and then
Yeah. Ansh, it sounds a bit distant. You sound a little bit distant on your audio, but I think I got the key thing, which is the stimulus opposite in direction, right? So Tanisha, take it away. What is the stimulus opposite in direction?
So the volume is changed for all of the things,
Is
the
changed,
species,
is changed what I want to hear?
reduced.
Good, because if you're not specific, you will get the answer wrong, right? So remember, volume was decreased. So what's happened to pressure?
So the pressure has increased.
Good, and let's quickly write the equation. N2 plus H2 gives you NH3. Balance this for me, Tanisha. What do we end up with?
We end up with 3 on the H2.
Yep.
And then 2 in front of, yeah.
Good, and it's exothermic, so we can add a quick heat there. Good. So how many gas moles do we have on the left and the right?
On the left, we have 4 gas moles. On the right, there's 2.
Good. So we're trying to decrease pressure, which is the opposite of increasing pressure, right? So we've decreased volume or we've increased pressure. The opposite is decreasing pressure. So you want to favor less gas moles. So are we going to shift to the left or the right?
We're going to shift to the right.
Good. So we're going to shift to the right-hand side. Good job, right? So what that means is that your ammonia should increase and your hydrogen and nitrogen should decrease. That should be the end change. All right. Now, when we're talking about these concentration time graphs, Pranav, what are the 2 phases that I explained to us?
Well, there is the stimulus phase and counteraction phase.
Good. Now, what will dictate how much these concentrations will change in the stimulus phase, Pranav?
How much like the volume has decreased by.
Okay, so the volume was reduced. We don't know how much it's decreased by. So what might you like to do?
Maybe like, do we like set like how much it has been decreased by ourselves or no?
Yeah, you could. You definitely could. That's a hard part about this question, right? A lot of it's in the air. So it's all very vague, right? You can assume that the volume is halved, but if you assume the volume's halved, everyone, do you agree the concentration of hydrogen would be up here, which is way outside the graph? So you can't do that in the HSC. So I'd say rule of thumb, you can just ballpark that aspect of this graph. So you can say hydrogen increases by, let's say, this much, right? And that would mean your nitrogen would increase by a little bit less, and your ammonia would increase by that much. You're not going to lose marks for this because they have not been specific. But remember, if they did tell you the volume was halved, you'd have to double the concentration. That is the principle, right? Good. So you can just ballpark it around there, as long as you show that hydrogen increases the most, etc. Okay. Good. So you've done the initial stimulus phase. What about the counteraction phase? What do we do now? So let me ask, this is a little bit tricky, so I want you all to think hard about this one because you can make mistakes with this. So let me ask Riyasat, how do you know how much to decrease everything by or increase everything by? Is there anything you're cautious of when you're doing this?
I'd look at the stoichiometric ratio of all three, all the particles species.
Okay. So we see the ratio is 1 to 3 to 2. Now what?
If we first I just did hydrogen and I decreased it gradually by a certain amount.
Okay. All right. So tell me this: did your curve, did it decrease like this, or did it decrease like that? A or
A, I'd say A because.
Good. And why not B?
I'm not entirely sure for the reason of this, but I did I did forget what the reason was. Yeah.
No worries. Can anyone tell me why, if a student did the curve in B, they would be incorrect, the curve in A would be correct?
Is it because it can only partially counteract the change, so it wouldn't go back to normal?
Very good. Good job, right? I stressed this so many times for a reason, and the reason was in LCP, you can never completely counteract a change. And B is not just completely counteracting, it's going in the opposite direction, right? That's extreme counteraction. That's impossible. Okay? So if a student does that, immediately tells the examiner you don't understand LCP. So it always has to return to a baseline that is above the initial concentration, because you want to show a partial counteraction of that change, right? So very good. So, okay, we could pick A. And so now what you'd do is you'd pick a random decrease as long as it's partial. And then what you'd have to do is, okay, you'd get a ruler out, everyone, and you would measure how many centimeters you changed your hydrogen by. So I want you all to calculate. You get a ruler out, how many centimeters did you change your hydrogen by? Let's say I changed it by, I don't know, 2 centimeters. What do I do next? Let me ask Athava, what happens next? All right, I might ask Mithilesh, what happens next? I know that hydrogen, I've decreased it by 2 centimeters in my graph. What do I do next?
Okay, I would do ammonia next. So,
Good.
sorry, nitrogen. I do nitrogen next. So
Okay.
it would decrease by 2 divided by 3 centimeters, so 0.7-ish centimeters.
Yeah, so what you can do very quickly is, right, okay, well, 2 centimeters, how many parts in this cooking recipe did that refer to? That referred to 3, right? Because there's a 3 in front of hydrogen. So a change of 3 parts in my stoichiometric ratio is 2 centimeters. Maybe this will tell you, if you want to make your life a little bit easier, you can change this by 3 centimeters to make it an even number. So let's say I did that. I saw 2 centimeters gives me odd decimal. So I'll say 3 centimeters is 3 parts. So I now know changing by 1 centimeter is 1 part in my stoichiometric ratio. So hopefully that makes it easier. Now, Mithilesh, you're completely right. Your ammonia should go up. That means your hydrogen and nitrogen, as we said, must go down. So your nitrogen, you're going to decrease it by how many centimeters now, given that I've changed the key?
Oh, okay. 1 centimeter.
Good. So you would make sure that the decrease is by 1 centimeter. And what's the other thing you'd make sure? They all return to equilibrium at the same time point, right? So that's the second thing I'd want to be considering. Very good. Now, what about ammonia? What's going to happen there? So we'll come back to Riasat. What's going to happen to the ammonia?
So looking at the stoichiometric ratio, there's two parts of ammonia, which is 2 centimeters equals 2 parts. So it would increase gradually by 2 centimeters up to the time of equilibrium when it goes back straight again. Yeah.
Yeah, very good. So you could show it something like this. So it increases by, let's say, 2 centimeters now. Okay, and it'll return to equilibrium. Reset, what would happen if, let's say, the ammonia, let's say I did 2 centimeters, but it crossed the nitrogen just due to the positions of everything? Is that correct? If the ammonia crosses the concentration of nitrogen?
I would say it can be correct.
Yeah, completely right. Remember, we don't care about concentrations being equal. We don't care about concentrations crossing each other. The only thing we care about is they become constant at equilibrium. That's it. Okay? And then in the counteraction phase, the change in concentration must follow the stoichiometric ratio. It's that simple. Very good. So everyone, this is the hardest that a concentration time graph can get. I think you'll realize it's not that hard once you understand the key principles, right? Stimulus phase, dependent on initial concentrations. Counteraction phase, stoichiometric ratio. Get them back to equilibrium at the same exact time point. If you do all of that, you've got 4 marks. And I think the one additional thing you all learned here is to make sure to highlight that it's a partial counteraction. So you can never completely counteract the stimulus. So just pay attention to that. Okay? But very good. Does that make sense to all of us? Do you see how drawing a concentration time graph is a little bit different? You have to apply a few additional considerations. So does anyone have any questions at all? Did anyone do anything slightly different or have any questions about this graph? given that you've done it yourself as well now. Good. Good job. You've done one of the hardest parts of Mod 5, and that tells you Mod 5 is pretty much of a cruiser of a module, right? It's probably the easiest chemistry module to do. That's not a bad thing because they'll still test 25% of your exam will be on Mod 5 questions. So if you understand this well, it's 3 marks. Good. Let's move on. So you can do all these questions in your own time. We shall move on to... Let's quickly just look at this question. It's a very common question that pops up, and it will be testing your application of LCP. Because remember, the reason you're learning LCP in the real world is because 99% of reactions don't go to completion. And as a society, we may always want to maximize yield. So we can maximize how much of a product we make, so we can maximize the efficiency of its use in society, right? So they're asking for 4 factors that would maximize the removal of H2S in this reaction. And so I'm just going to go across and ask each and every one of you for 1 factor. Give you 10 seconds to think of the factors. So think really quickly. Okay, let's do this. So I'm just going to go across and ask each and every one of you one. So I apologize, it will get harder because students would have picked most of the options towards the end. So Gerald, starting off with you, what's 1 factor you could use? Now, Gerald, what is this question actually asking? It's asking how H2S can be removed from the system. So which direction are we trying to go?
We're trying to go in the forward direction.
Yeah, so the question is literally just asking, how do you shift the reaction to the right? They're just trying to make it sound a little bit fancier by talking about H2S. And so now you can't touch H2S directly, because obviously if you said we can maximize H2S removal by removing it, that's not, it doesn't mean anything, right? So that's the only reason they mentioned H2S. So you can't directly touch H2S, but we need to get rid of it, aka shift to the right-hand side. So what are the 3 stimuli we can apply, Pranav, to a system to shift it?
You can like it can be affected by temperature, concentration, and pressure / volume.
Good. So Pranav, what's the first stimulus you would use to shift the equation to the right?
I would use temperature. So I would decrease temperature.
Very good.
And yeah, exactly.
By decreasing it, we'll shift it to the right to increase temperature. So very good. So we could decrease temperature. Mithilesh, what's 1 more?
Increase pressure or decrease volume.
Good, right? So increase pressure, decrease volume. That would make us favor the side of less gas moles because we want to decrease pressure. And so that would be the right-hand side, which has 2 moles of gas, versus the left-hand side that has 3. Very good. Tanisha, 1 more?
Decreasing the SO2 concentration. Oh, sorry, increasing it.
Good. Increasing SO2. Very good. Because if you decrease SO2, you'd want to increase it by shifting to the left. So good. It'd be an increase in SO2. Good. And Risat, 1 more?
I said decreasing the concentration of H2O.
Very good. Risat, can I touch the sulfur?
No, I mean, it wouldn't change its concentration since it's a solid.
Good job. So that's what they're also testing you on. And there's 1 more we could do. Is it? Oh, we've got all 4 actually. 1, 2, 3, 4. Good job. That was everything. Good. So just be ready to answer these kinds of questions. And this is also very high yield, everyone, because Module 8, the last inquiry question, they will give you an industrial synthesis reaction, some kind of industrial reaction. You'll have to talk about how to maximize yield, how to increase the rate of reaction, how to consider the uses, location, raw materials. And part of that for yield, you will need to apply what you just did. So how can we maximize the amount of product we produce using LCP? So it's very high yield, you remember, and apply that knowledge. So good job. Let's move on. Okay, so we're already on to inquiry question 3, so good work. We're on to the equilibrium constant. So who wants to define what the equilibrium constant, which is K, that's the letter we use to denote the equilibrium constant, what is it actually representing? Next, before I even ask that, who's learnt this at school? Can you raise your hand? If you've learnt K at school. Good. Okay, so Gerald, maybe start us off. What is the equilibrium constant telling you?
The equilibrium constant tells you the relative concentrations of products to reactants.
Good. Relative concentrations of products versus reactants. Good job. Okay. What is that measuring? There's a term that we are measuring using K. Does anyone know what that is?
The reaction quotient, yes.
So reaction quotient is the exact same as equilibrium constant, except you don't know whether the system is at equilibrium. So if you don't know whether the system is at equilibrium, the same calculation gives us what we call a reaction quotient. And if it's equal to K, you're at equilibrium. We'll talk about that later. Let's push that aside for now. What is this measuring? I'm just looking for a word.
Is it ratio?
Yeah, that's what Gerald has mentioned, ratio of concentration of products to reagents. You all know this. I'm just
Is it
being
the
Position?
yield?
Not even yield, because it's not technically measuring yield at all. Because if you look at the actual formula, you start raising things to the power of the stoichiometric ratio. So it takes the yield out of the equation. Okay, you will know this. I'm just going to identify it. You need to mention it's a measure of equilibrium position. That's what you want to hear. And position is what Gerald has mentioned, which is the relative concentrations of products versus reactants at equilibrium, right? So the equilibrium constant measures the equilibrium position. So hopefully now you'll understand, and this is what I asked you all previously. When I say that the equilibrium position lies to the right, I think Mithilesh mentioned that the system is still at equilibrium, however the concentrations of products are fixed and at a high value, the concentrations of reactants are relatively at a lower value. What would that do to the K constant? So if the position lies to the right-hand side, do we all agree we said the concentration of products will be fixed and at a high value? The concentration of reactants will be at a lower value. What will that do to K?
It'll be high.
Yeah, very good. So when K is in its hundreds or thousands, you can say the equilibrium position lies to the right just by looking at the K value. Does that make sense? If K sits at around 1, if K is around 1, what does it tell you about the equilibrium position? Is it lying to the left, to the right, or to the middle?
The middle.
Yeah, it's similar concentrations. Given that we're raising things to the power of stoichiometric ratio, you can't say it's exactly in the middle, but it lies approximately in the middle. And I think you will understand now that when K is less than 1, that tells you that relatively you have more reactants or denominator relative to products. Okay, so it tells you the equilibrium position lies to the left. Good. So that's how you understand and eyeball the K constant. Now, to be very specific, everyone, if we are looking at this reaction here, the way you find the equilibrium constant is you must get the concentration of products. Do we see how C and D are our products? We need to raise them to the power of this stoichiometric ratio. So if there was a 2 in front of D, you'd raise D to the power of 2. If there was a 3 in front of C in the ratio, you'd raise C to the power of 3. And you would find the product of those two values. And you do the exact same for reactants. So technically, the stoichiometric ratio, or the K constant, is the product of the products raised to the power of the stoichiometric ratio divided by the product of the reactants raised to the power of their stoichiometric ratio. Okay? I think you all know this, so we might go straight to questions, but there is one thing they'd love to test here. And it's that only one factor out of those 3 variables, do you remember when I taught you the 3 disturbances to equilibrium? Only one of them can affect the K constant. And it's written here, so I'm not going to ask you, but it's temperature. That's very high yield to understand. Can anyone tell me why? What did you all learn at school? Why is temperature the one factor to affect the K constant? Let's go with who we've got. Who haven't I asked too many questions of? Mahe? Any ideas, Mahe?
I'm not too sure.
It's all right. Pick one of your friends to answer the question.
Mitty.
Okay.
Yeah. I'm not too sure, but maybe it's got to do with something like the. No. Yeah, I'm not too sure.
Yeah, so it's a little bit hard to understand until you look at the concentration time graphs. And remember, I stressed this all to you. When you look at temperature, what's the one unique thing that tells you that temperature was the stimulus, everyone? So let me rub all this mess out. Look at the graph yourselves. So T3, we said temperature was the stimulus. What happens?
There's no stimulus phase to it.
Yeah, very good. So I think you'll realize what happens is that you have an initial stimulus phase where everything is disrupted, and then everything returns back to a ratio that will aim to preserve the K constant, aka not change it, right? Very similarly, when we disrupt all the pressures, we have this huge stimulus phase which disrupts the K constants, but eventually things will return back to equilibrium. And that K constant value, when you plug everything back in the formula, will be the exact same K value. The only difference is temperature. There is no initial stimulus phase. So what happens is, you'll see the ratio of everything permanently changes. Right? So have a look at this. Your hydrogen goes permanently up and it stays at that fixed value, and your nitrogen goes complementarily down, and your so that's your hydrogen. So what I'm drawing now, this is your H2. This permanently increases. So you can see that all of the chemicals have been permanently shifted, right? And that's going to change the K value. So the simple answer is temperature does not have a stimulus phase, only a counteraction phase. And this is going to permanently change the ratio of products to reactants, and thus the K constant. For all of the others, what the counteraction phase is doing is restoring K after that initial disruption. Initial disruption, we restore K. Initial disruption, we restore K. But here, the initial disruption never affects K. It's the counteraction which is going to go and change your K value. Okay, so hopefully that makes sense to us all. Any questions so far? They'll never ask you this, by the way. There will never be a HSC question asking you to explain why temperature is only factor, but hopefully now you understand why. Okay, good. All right, let us move on. So we were up to, let's go down to K constant questions. Good. Now, can you raise your hand if you've done a few K constant questions? So I know, or Bob, you said you've gone ahead at school. I know most of the Sydney boys students have done this. Holston, Pranav, you've done K with me, but have you done it at school as well, just to get what the pace is?
Yeah, we've done like a bit of it.
Good. And Tanisha, what about you?
We've just started it. So like our Friday lesson, we went over what it is and stuff.
Okay. And I guess last person, Athava, learnt K yet? K constant?
We just started module 5, so I think we're still on the Gibbs free energy.
Oh, okay, right. Well, I guess
Yeah.
what I'll do then is to help you all out. We'll do one K constant question that's easy, and I'll go straight to hard ones after that, okay? You realize K constant questions are very easy, right? We'll just do this one, just so I can teach you all how to understand this. If I was to find the K constant for this, remember it's products, so your products are here, but what consideration do I have to make? Because this is an area of silly mistakes for students. So we'll go to Gerald. What's one thing I'll need to consider when I'm writing products in K, Gerald?
You need to take a H2O because the concentration of liquids, pure liquids, are constant.
Yeah, very good, right? So this would just be Cr2O72 minus in aqueous state. It's got a 1 in front of it, so I don't care about anything else. Confirm that both of these reactants are not solid or liquid, and that's the case. So we'll do CrO4 2 minus, and we'd raise it to the power of 2, because you'll see the 2 in front of it in the ratio. And we'd multiply it by the other reactant, which is H plus raised to the power of 2, because there's a 2 in front of H plus. So that's very quickly how to do an equilibrium constant. And they'd give you all the values, you just sub that in, put it in your calculator. Okay? Athava, does that make sense as to the one thing you need to consider when you're writing K? The one thing I'd ask you to be cautious of is states. Okay, we do not include no solids or liquids in K.
Yeah. I just have a question.
Yeah.
So like, what do you exactly put in the calculator?
So what they'll tell you is a concentration of this is X moles per liter. So the unit will always be moles per liter that you'll be inputting in Athava. Okay?
Right.
And
Okay.
you'll just be calculating concentration in moles per liter.
Yeah.
Yeah.
Because they give you like the moles of each one of them, and then they tell you to calculate it.
Yeah, how about I give you a question and you'll see, because the best way you'll understand this is through exam questions. So let's do this. I want to give you a harder one, but these are not too hard. Here is a question. What I'll do is I'll let you all have a look at the question first. I'll zoom out. Okay, and I guess before I give you this question, the one thing I want you to understand, I want everyone to read this question. And those of you who've done the K constant, I want you to tell me what in this question tells you need to use a rice table or an ice table. Those of you who haven't done the ice table, don't worry about that yet. Those of you who have done it, how do I know I need to do an ice table? One of the big dilemmas that students seem to have.
Okay, so it says initially, and then afterwards it says at equilibrium. So
Very good. So I guess the key point that Mithilesh has highlighted is whenever they give you concentrations at different time points, you must use a rice table. Now I'll go through what a rice table is now. Okay, so a rice table is a little mnemonic, and it's an acronym where R stands for the stoichiometric ratio, I stands for the initial concentrations, C stands for the change, and E stands for the equilibrium concentrations. And the principle here is when we are subbing those values into K, we can only sub in equilibrium concentrations because we are trying to find a constant of equilibrium. Does everyone agree? Now, you all learnt this from concentration time graphs. But what is the change in concentration dependent upon?
Stoichiometric ratios.
Yes, very good. It's the same exact principle here, guys. You can't forget that. Very good. So let's apply it in this worked example question here. So do a very quick rice table. RICE. You write the equation. So we've got 2HI going to H2 plus I2. And remember, we are only subbing in concentrations for initial, change, and equilibrium. So our initial concentration of what substance is 0.8? Everyone? What substance has a concentration of 0.8?
HI.
Yeah, very good. Because you can see that HI is decomposing to form your products, right? So initially, imagine time equals 0, right? HI has not engaged in any collisions. Imagine you froze in time. You have 0.8 moles per liter of HI. And Athava, what can you say about H2 and I2? Have there been any collisions of HI yet to form any H2 or I2?
No.
No, so at time equals 0, we can say the initial concentrations of H2 and I2 is 0. And the ratio is just 2 to 1 to 1. Okay, what's the next thing that you get from this? You've been given temperature. Does anyone know why you've been given temperature?
because the value of the equilibrium constant changes with temperature.
Very good. So they'll always give you a temperature for questions. It doesn't mean you have to use it. It just tells you at that temperature, that's what the K constant is. Very good. Good job. All right. So now you've been told at equilibrium, there's 0.0884 moles per liter of hydrogen. So we're going to go to H2. Right. Equilibrium, there is 0.0884. So how much has hydrogen changed by, Pranav?
0.0884.
Good. So what I'm going to do now is I'm just going to write outside of this table, I'm going to write that, well, 1 part in this cooking recipe or stoichiometric ratio, 1 part change represents 0.884, just like how we did in our concentration time graphs. So 1 product increased by 0.0884. Resat, what must the other product increase or decrease by?
The other product must also increase by 0.0884.
Easy, right? And what about the reactant? What must it decrease by? So go back to Gerald. What must our other HI decrease by?
It must decrease by double. the
Yeah,
amount.
very good. So we can do negative 0.0884 times 2, or like just directly put in whatever that equals to. All right, very good. So what is our equilibrium concentration of HI, everyone? Can everyone do 0.800 subtracted by 0.0884 times 2? Because remember, it's 2 parts. There's a 2 in front of the HI, so it must change in concentration by 2 parts. Someone quickly tell me what's their answer for the equilibrium.
0.6232.
Okay, 0.6232. Now, straight away, you'd want to store this as a value. So I'll store it as A. So make sure you never round things off to the very, very end. Okay, so what's my K value now? So K value is just your products, H2 times I2 divided by HI squared. And that's going to be equal to 0.0884 squared divided by A squared. Okay, because A was a concentration of HI, and we're squaring that as well. So what do we get now? What's the answer for K?
.0201.
Good. Okay. And so, Mithilesh, what does that tell you about the equilibrium position? Because whenever you get a K value, pause and think conceptually as well. Think, does this make sense? So where does the equilibrium position lie?
Like quite a lot to the left.
Yeah, so you'd say there's very little reactant, and there's a lot of, very little product and a lot of reactant because it lies to the left. Good job.
I have a question.
Yep.
You know how you squared the top one?
Yeah, I squared that because H2 is 0.0884 and I2 is 0.0884.
Oh,
So
because you, okay, yeah.
yeah, it's the same as squaring it, but yeah. Good. It's just because they were equal concentrations. Good. Good question. All right. So that was your simple questions, everyone, but I can almost guarantee you in your HC it will never be this easy. Okay? That was just a bit of an intro to how to use a rice table. Remember this. If you are ever given concentrations at different time points, you must use a rice table. This is a universal rule, and it's something that you'll be applying every single time you do a HSC question. So these things you cannot forget, otherwise you'll get stuck. And it's easy now because you're only looking at mod 5. But imagine if you get a long-winded question, which is a bit of mod 8, a bit of mod 7, and a bit of mod 5, you might forget to apply the rice table. So it's a very important rule for you to remember. So maybe write it in red or highlight it. Okay, let's move on. Let's do this question. This is more like an exam question that you'll get in school. So I'm not going to say anything. I'm going to see how well you can think your way out of this situation. So you all have about a minute to do this question. Give it a go. Can we get some water? I'll be right back. All right, let's take this away. So how did you go for this question? So we'll start with Maher. What do we do for this question?
So I wrote out an rice table.
Pause for one moment. When do you know you need to use a rice table? What did we say? I circled it in red and I told you. You know you need to use a rice table when? The most important thing from this lesson, there are 2 very important things that you need to quite literally tattoo into the recesses of your mind for chemistry, okay? And if you forget this, I'll make you do a physical tattoo as well. It's that concentrations at equilibrium are constant, and in the counteraction phase, they will change based on the stoichiometric ratio. So point 1 is concentrations in counteraction phase dependent on stoichiometric ratio. The second important thing is you do a Rice table when you're given concentrations at different time points. Maya, are you even given any concentrations here?
No.
No. So do you think you need to do a Rice table?
No.
No, right? So this is how you navigate through chemistry questions. You find principles, you stick to the principles, no matter what question's thrown at you, you follow them, and you'll always get your answer. So here, I'm telling you right now, you don't need to do a Rice table, okay? That's because there's no initial or equilibrium concentrations. So what we might like to do then is follow our basic chemistry knowledge, right? In any chemistry question, we write the equation and then our data. So let's do that. I know they've already given you the equation, but let's identify them together. So we've got 2HI breaks down into H2 and I2. Please do states. I'm going to skip that for now. And we know that K for this, we'll call this equation 1, and we'll say K1 is equal to 0.0201. Now we've got a second equation, and we'll call this is HI gives you a half H2 plus a half I2, and they're asking for K. So K equals question mark. Do you all agree this is what the question is? Right, you want to convert all of these English into chemistry, otherwise it's a bit hard to understand. Now, do you all agree it's the exact same equation? Shouldn't the K constant be the same then? Why is a K not the same? Well, logically, what's overtly different about these two reactions? There's one salient difference.
The stoichiometric ratio.
Yeah, very good, which is going to affect how much you raise things to the power of, right? Because that's part of the K constant. So the stoichiometric ratio is what makes things different. Okay, next, what do you think we do? So what do I do now? So let's say I'm stuck as a student. What would I do now, Ansh? What's your plan of attack?
We write the K equation again. What would
Yeah.
we?
For both of them. So let's write for K1, what's the expressions? It's for the first equation here. Ansh, what do we get?
H2 times I2 over HI squared
Equals to? Yeah, 0.0201. So we want to identify that. So that's what K1 is equal to. So what's the expression for K2, Mithilesh?
K2. Oh yeah, it's the square root of K1.
Yeah, very good. So that's a very important thing to pick up here. So what we're trying to do is we're trying to find this unknown K in terms of our known K, which we know the value for. That's the plan of attack here. So find unknown K in terms of known K. In terms of known K. Very good. So we can then say that K2 is quite literally the square root of K1. You all notice that? That we've square rooted the numerator, which is half, that's the same as square root. We square rooted the denominator, which was square root of a square, which would just be raised to the power of 1. Good, so that's root of 0.0201. So what's our answer?
0.142.
0.142. And how many sig figs do we need here?
Three.
4.
3 or 4? What do we think?
3.
How many sig figs is 0.0201?
Yeah, 3.
3? Are we sure? Gerald, what do you think?
I thought it was 3 as well.
You thought it was 3 as well? And what about Riyasat?
I think it's 3 as well.
Okay, right. 0.01, how many sig figs is that?
2.
2?
Isn't the 0 also mean something?
So if it's 100, in maths we say that's 1 or 2 or 3, depending on where the rounding was done. But in chemistry we say it's 1. We always assume the lowest number of sig figs, right? But zeros after a decimal point are always significant. So if it was 0.0001, those zeros are significant after a decimal point, right? So it should be 4 significant. But good. So the answer should be to 4. Round off to 0.142. So what's after the 2?
It should be 1418.
Yeah.
1418. Okay. Now this doesn't really matter, everyone, especially for a k constant because it's unitless as well. So you would get full marks for this. I'm just being very picky so that you have the sig figs as well. Good. All right. So you can do all the remaining questions in your own time, but let's move on to doing some exam style questions. Okay. So let's move on to going all the way down to here. And I'll give you all a k constant question to attempt. To question 2. Question 2, and we'll do question 3 together. Okay, so this is from the Balcom Hills with 2019 paper. So give this a go. Okay, let's start going through this question. So we've been given the equation, and we've been told that this number of moles was placed in this vessel so that equilibrium could be achieved. So what time points do we see here? So we have the number of moles, so little n, of phosphorus pentachloride, so PCl5. Is that the number of moles initially or at equilibrium, everyone?
Initially.
Yeah, very good. So you can write Pn of PCl5 initially is 0.2. And then we can write volume of the vessel is equal to 2 liters. Okay? And so you've got an N and a V. You can almost start to see what we need to find now. So then we can say the container was found to have 0.5 moles of chlorine gas. So we can write N of Cl2 is equal to 0.15. And what was this? Is this equilibrium or initially?
Equilibrium.
Yeah, very good, because it takes until equilibrium to get your chlorine gas as well. Okay, so good. We can start subbing things into our rice table. So we can do a quick rice table here. So PCl5 goes to form PCl3 and Cl2. It's all got a 1 to 1 to 1 ratio. Initial concentration of PCl5. What is the initial concentration, everyone?
0.1.
Yeah, good. So you can write 0.1. Good. So we're at 0.1. And what was the equilibrium concentration of Cl2?
0.075.
Yeah, we could do 0.15 divided by 2, which I believe is 0.075. And that, we'll write down here, 0.075. The initial concentration of Cl2 is 0. So what has it increased by?
Sorry, could you say that again?
So your Cl2 is now 0.075, and it was initially 0. So it's increased by 0.075. Do we all agree? So how much should every other substance change by? So what about PCl3?
You should increase by 0.075.
Yeah, it was initially 0 as well, because remember, at time equals 0, we have no products at all. And what about our PCl5?
It will decrease by that.
Yeah, very good. So you can do 0.1 minus 0.075, whatever that is. Okay, so then you can say K is equal to your PCl3 times your Cl2 divided by PCl5. And that's going to be equal to 0.075 squared over 0.1 minus 0.075. What do we get?
0.225.
Good. So the answer would be A for this. Very good. Good. And, sorry, I wanted to just clarify this. The 0 here, that should not be significant. So apologies, that was my mistake. For the previous question, 0.075 is 2 sig figs. Yeah, so it's zeros between numbers. So if it was 0.0705, that's 3 sig figs. Okay, so my bad. It should be for the previous question, I think it was was it 0.421, I believe, or 42412, something of that sort. That would be 3 sig figs, and you'd keep your answer at that amount. So good. So zeros after a decimal point, if it's before a number or an integer, then it's non-significant. Good. Okay. Anyway, coming back to this. Good. So the answer is A. So these questions are not too hard. I think the only thing you have to realize is if they give you moles, please do not input that as concentration. That's a really like a band 2 or band 3 silly mistake you can make. Okay. So that's why you should always put your data first. Equation, data, and then you start finding your concentrations. Good. I'm going to use this question to teach us Q. Now have a look at how the question is phrased so you understand what Q is all about. Now, let me rub everything out for us. Risa, what does Q represent? What's the name of Q?
Is it the reaction quotient?
Good. So Q is your reaction quotient. And when do we use Q and when do we use K? Because the formula for Q is the exact same as K. It's products raised to the power of their stoichiometric ratio divided by reactants raised to the power of their stoichiometric ratio. So you can say same equation as K. But when do we use Q? When do we use K?
We use Q to check if it is at equilibrium, because if Q equals to K, then the reaction is at equilibrium. The system is at equilibrium, and we use K when we know that the system is already at equilibrium.
Very good. Good job. So when you're unsure whether a system is truly at equilibrium, you can determine and find a Q value. And if Q is equal to K, well, obviously it's at equilibrium. Mithilesh, what if Q is greater than K? What does that tell you? Which direction is being favored to reach equilibrium?
The left.
Yeah, very good. And I guess the way you can very quickly think about this is if you draw it on a number plane, you always want to get to K. So if Q is greater than K, you're going to favor the reverse reaction to get back to K. And contrastingly, when Q is less than K, Athava, is it at equilibrium?
Pretty sure not.
No, yeah, because Q equals to K, only then are you at equilibrium, right? Because K is the quotient only when a system's at equilibrium. So if it's non-equal, it's not at equilibrium. In which direction do we go, Athava, to reach equilibrium?
The other way to the right.
Yeah, so Q is here, or less than K, and K is greater than Q. You want to favor the forward reaction, or you want to favor the right-hand side to return to K. Very good. Good job. So we might quickly do this question. It's quite an easy question. This might be our only question on Q because Q questions are very easy. It's quite literally also rice table, finding the exact same expression and just comparing it to the K value there. And I think we all know why they've given us, well, they should have given us a temperature. They've just written here at a certain temperature, and that's because K is temperature dependent. So do we do a rice table here or do we not do a rice table here, Ansh?
We wouldn't use a rice table
Okay, you wouldn't use a rice table, and why is that?
because we're not getting concentration after.
Yeah, very good. There's no two different time points. Does everyone see that? There's only one time point, that this number of moles of O3 and this number of moles of O2 were just introduced into this vessel, right? And which direction is it going to go? So forget about equilibrium right now. They will eventually reach equilibrium, but initially, is it at equilibrium? So all you've been given are data about initial time. You've been given no data at equilibrium time point. So you don't have to do a rice table, just sub it straight in. So your K is just equal to O2 cubed divided by O3 squared. And remember, you just want to find the concentrations here because you've been given a number of moles. These are all N values. So what's the concentration of O2? It's what's 1.5 divided by 5? Is it 0.3?
0.3.
Okay, so 0.3. That's of O2, just confirming. Yep. and cubing it. And your O3, what's 0.3 divided by 5? The 0.06.
0.06.
Good. 0.06. Where's the squared? What do we get?
7.5.
7.5.
Good. So which direction are we going to go to favor and reach equilibrium, Gerald?
To the right.
Good. So we're going to say, well, Q is less than K. So we want Q. We're going to favor the forward reaction to reach K. Good. I think you're all realizing the first couple questions in a trial paper are always pretty easy. And that's because it's kind of like warm-up questions. You will typically see that as you go down, you'll start to notice the questions become a little bit more and more comprehensive or application based. So again, you can do these questions in your own time as well. So like I said, all these exam questions all need to be done by week 10. So these are at about 50 pages of exam questions at the end. And these, I would say, are even more important, everyone, than your, especially these. Like I don't care about you doing your textbook questions. They're only there just so you know you have access to textbook questions. You can skip these pages if you feel confident with your theory, but I want every single question of these trial pass papers done. Okay, that's your main homework. Good. All right, let's come down now. We've done K, we've done Q, and see this question. What is this? It's also Q. It's also easy. It's easy. Yeah, I don't think there's any use going through many other Q and K questions. Are you all confident? Can you raise your hand if you feel confident with Q and K calculation questions? And if not, I'm more than happy to do one more question, etc. And if you do feel a bit unconfident, do let me know what it's regarding. Good. Gerald, are you confident with K calculation questions now? Good. And Tanisha, how about you? Good. And Rabab?
Yeah, I'm fine.
Okay, good. All right, good job. All right, now quantitatively analyzing the K constant, right? We've already spoken about this dot point here, right? Qualitatively analyze the effect of temperature on K. It's quite simple. It all depends on whether the reaction is exothermic or endothermic, right? So let's say the reaction is exothermic. When I increase temperature, what's going to happen to K, everyone? I'll get a... Let me get Pranav. You explain that to us.
So if you increase temperature, it's gonna like the opposite decrease. So it'll favor the endothermic reaction. So K would be less than 0.
Okay, you don't want to say ever less than 0 because K should never be 0, right? It should never be negative because that tells you the reaction has gone to completion or it's not at equilibrium. All you'd want to say is, did K increase or decrease? So you just want to say here that an increase in temperature would result in the system trying to partially decrease temperature by favoring the endothermic reverse reaction. And this will decrease the concentration of product, increase the concentration of reactant, and thus you'd lower your K. Does that make sense? That's what this entire dot point is all about. So can you make those conclusions? And maybe I'll ask, who else we got? Athava. If we've got an endothermic reaction, if I increase heat, what will happen to K?
The system will favor the exothermic reaction, and then that will.
Okay, I've increased heat. Would it favor the exothermic reaction?
I mean, it would favor the endothermic reaction.
Okay, good. So, okay, we've increased heat. So the system wants to decrease heat. And how do we do that? By favoring the?
Endo.
Yeah, the forward endothermic reaction to get rid of heat. Very good. And so what's going to happen to K now?
So there will be an increase in the products and decrease in the reactants, which will lead to a higher number. Okay.
That's it. That's it. Easy, right? So that's what they mean when you qualitatively are explaining the effect of temperature on K. Do you all agree it all depends on whether it's endothermic or whether it's exothermic? Okay, that's it. So we're not going to talk about a dot point much. It's a very easy dot point. This is high yield, and I'll give you all a hint. So the average mark in the Mod 5 exam last year, and it was sat by a lot of bright students, was around 60-ish%. And the question that most students got incorrect was a question about spectroscopy. So I want you to remember this dot point, very high yield, and it's going to be in your exam. So when we're talking about actually measuring equilibrium in the school lab setting, does anyone have any idea how we can do that? How do we measure a K constant in the real world setting? Because we might have initial concentrations. I can give you 1 mole per liter of reactant A, 1 mole per liter of reactant B. But how will you know how much of A and B got used up and how much C got formed? Is there any way we can do this? I want you all to think hard. Any ideas? Mithilesh, have you read up on this dot point?
No. What I'm assuming is you just let it react.
Yeah, but the issue is when you let it react, if everything is colorless, you'll have no clue how much product you've formed or how much concentration of your product you have. So I guess the tip that I'm giving you all is the only way we can measure equilibrium concentrations and thus get K is when we're dealing with colored solutions. This is a very important reaction because it comes up over and over again, and in module 8, it's going to return. This is an iron thiocyanate equilibrium. And what happens is iron 3 ions, which are characteristically yellowy brown in color, they're going to combine with your colorless thiocyanate ion. This is a polyatomic ion consisting of your sulfur and also your cyanide. So it's a thiocyanate ion, and it's got a valency of -1. It's important to remember that. What happens is it's going to form a complex. Does anyone know what a complex is? You will need to formally define it in Module 8, but for now, Pranav, any idea what a complex is?
Is it something that forms from like a
Thava, what's the color of copper? Copper 2 in solution. What color do you typically see?
I can't remember.
Who can tell me? Copper 2 sulfate. What color?
Blue.
Very good. Right. Iron thiocyanate is going to be red. Iron 2 hydroxide will be green. Iron 3 hydroxide will be brown. Is anyone noticing a pattern here? What kind of metal is causing it to be a colored species?
The
Transition.
Yes, very good. Transition metal. So a complex is a colored species that is produced from a transition metal in solution. That's all I want you to know for now. So transition metals give rise to all sorts of funky colors, and typically your complexes will have this overall charge as well, right? So here we've got a complex. This is an iron thiocyanate complex. And it makes sense. We've got a +3 combining with a -1. The overall charge of this complex should be +2. Does that make sense to all of us? Now I want you to remember this. This complex has a blood red appearance. Blood red. Okay. Now the principle is, everyone, let's do a quick rice table in our heads, right? Let's do a very quick rice table in our heads like this. Right? Do we know the ratio for this reaction? Yes or no? Yes.
Yeah.
Would we know the initial concentrations if we are doing the experiment? Would we know the initial concentrations of iron 3 and thiocyanate? Yes, because we would be putting those solutions in your beaker or your colorimeter or whatever that is. Would we know our equilibrium concentration of iron thiocyanate? We know the initial concentration of iron thiocyanate is 0. Does everyone agree? Right? Because there is no iron thiocyanate formed at time equals 0. The hardest thing to do, and this is the only thing we need, does everyone agree, is the equilibrium concentration of iron thiocyanate. That's what we need. If we can find that, what we can say is therefore this increased by plus x is subtracted by minus x. So now I know all of the equilibrium concentrations. I can therefore find K. So the one thing you need to find is the equilibrium concentration of any one of those substances. And in our case, we're going to find iron thiocyanate. And the method by which we find the equilibrium concentration of iron thiocyanate is a technique called spectrophotometry. Spectrophotometry. What does that mean to you? It's a funky word, very long. It's a huge high yield part of Module 8. Half your data sheet is spectrophotometry data. So what is spectrophotometry? Break down every word for me. We've got spectra, we've got photo, we've got metry.
Okay. So spectra has got something to do with like seeing. Photos, light, and metry is like analysis.
Very good. Good job, right? So this is telling you that we are going to be either shining light or looking at how light is absorbed by a sample and measuring that to determine characteristics. That's what this is all about. So spectra refers to spectroscopy, right? So spectroscopy and spectrophotometry are all about spectra, and spectra can be divided into absorption spectra or emission spectra, and that just refers to light being absorbed by a sample, light being emitted by a sample. And we'll simply be measuring that. That's what spectrophotometry is all about. Light interacting with matter, and we're measuring stuff about matter. Does that make sense to all of us? Okay, so let's go into a bit more detail. The specific type of spectrophotometry you'll be using, because there's so many different types. At school, you'll be using colorimetry for this experiment. There's many other types, some which are way too expensive for school, such as atomic absorption spectroscopy, mass spectroscopy, nuclear magnetic resonance spectroscopy. We are going to be doing colorimetry because it's a very cheap, direct way, and we can look at colored species. Now, why is this solution red? And it's not a philosophy question, it's a science question. Maybe look at all your shirts right now. So why is Gerald's shirt white? Why is Mithalesh's shirt darker? Why is Risat's shirt bluish in color? What makes things a particular color according to light? So just look up at your room. There'll be a source of light up there. And that's white light, which, as you all know, consists of all the wavelengths of the visible spectrum. So that's around 400 to 900 nanometers. Why is your shirt a specific color? What is that shirt doing, and what are you seeing? Who wants to explain that to me?
Well, basically, like the white light is hitting the object, and then it absorbs all of them, but reflects one. So for the iron thiocyanate, you'll absorb all the white light except the blood red, and you'll reflect that out, which hits our eyes, and that's what we see.
Very good. Good job, right? So the blood red nature of iron thiocyanate is because it absorbs every other color of the visible spectrum except for red. And that red gets reflected and detected by our eyes in our retina at the back of our eyes and decoded as the solution being red in color. So technically, if you look around the world around you, all objects are actually the inverse of the actual color, right? Because that's the color they're actually absorbing. They're only reflecting the color that you see. So that's what they don't like or they don't absorb. So it's quite interesting. But the reason that I brought this up is because when we use colorimetry, this is what the apparatus looks like. So you need to get used to this, right? So the colorimeter, it kind of looks like a box, like a little rectangular box. It kind of look, maybe, can you all search, get your phone out and search colorimeter. You'll see all these images of colorimeters. They're just little boxes, and they have a bunch of dials and buttons, and you can place a solution in the box. Okay, and inside the box, this is what's going to be inside of it. Okay, so your solution will be placed in here. And what will happen is a light source will be emitting light into that colored solution. So remember, what color was our iron thiocyanate? It's red in color. You'll agree? So what's going to happen is that we're going to use a light source. Now, what's going to happen is a lens is going to be used to focus the light, not too high yield. So it's just to focus the light. What's important is we use a monochromator. Does anyone know what a monochromator does? What do you
Is
see?
it like
the
split?
light?
Is it like split the white
Very
light?
good. So physics-wise, it's called diffraction, but we are splitting that light into all of its constituent wavelengths, right? And what we're doing here is we are only allowing a specific wavelength to pass through that solution. Now, in chemistry, they love asking you this question. If the solution is red, any idea what color of light will be passing through the solution? Will it be red light or will it be the complement? Let's say it's blue.
The red light. I mean the blue light. I think.
Tanisha, you seem very
Wait. It would be green, not blue, because that's the opposite on the color wheel. But yeah.
Yeah, so yeah, the thing is, I don't know the differences in color, and you don't need to know the complementaries in the color wheel, but yeah, I guess that would be the case. I think they actually use blue light in this case. Let's have a look. Yeah, so for iron thiocyanate, we use a blue light, and I guess green would be more complementary, but blue is sufficient to determine the absorbance of light. So I guess the key principle I'm trying to get across here is you want to use the complementary color to the solution. Complementary color to the solution. Okay, now there has been exam questions where they give you a color wheel that makes your life easier because then you can just pick the opposite color on the wheel. So color wheel looks like this. There'll be one color on one end and the opposite color on the opposite end. And if this is red, there might be, let's say, green on the other side, and you would pick green. But otherwise, you aren't required to memorize this as long as you remember the inverse color to the solution will be passed through that solution because it's the inverse color that's absorbed to the maximum intensity. The inverse color is absorbed to the maximum intensity. Okay, very good. Now I want you to pay attention to this. It's quite important. What we're going to do now is we calculate a value known as absorbance. Absorbance. Okay, and the way we calculate this is we log the intensity of light before it passes through the sample versus the intensity of light after it passes through the sample. So in this case, it'd be IT. Now, let's just apply a quick thought experiment. Imagine there was 100% absorbance before it passed through the sample and 30% absorbance after it passed through the sample. What would our absorbance value be, everyone? So if the pre-absorbance intensity was 100% and then post-absorbance intensity was 30%, what's log 10 of 100 divided by 30? Quickly.
Negative 0.52.
Is 100 log?
No, it's 1.52.
Yeah, it should be 1.52. It shouldn't be a negative value. Absorbance should always be positive. Okay, good. So it's log of your before passing through the sample and then divided by after passing through the sample. Good. So Mithilesh, does this absorbance tell you anything? If I said Mithilesh, the absorbance of X solution is 1.52, can you tell me concentration straight away from that? No, you can't, right? So what we have to do now is we have to apply a very famous chemistry rule. This is a law of chemistry. It's called the Beer-Lambert equation. Has anyone heard of this equation before? Okay, so the Beer-Lambert equation basically states that the absorbance of a solution is directly proportional to its concentration. Right? Absorbance of solution is directly proportional to concentration. Now, Pranav, what can we swap this fish sign or directly proportional sign with, according to maths?
1 over.
or not 1 over,
Okay.
yeah, just equal to k, right? So we can now say that there's some proportion, there's some constant of proportion. It's kind of like a y equals mx. Do you all agree? If y is directly proportional to x, we can say y equals to mx. It's the same thing that we're applying here. We can say A equals to kc, right? Now, we have absorbance at this moment. Does everyone agree? We've got absorbance. We need to find concentration. What do we need to do to find our concentration? What value are we missing?
Okay.
K, very good. So we need to somehow find K, and do you all agree for y equals mx, K is just a gradient of a line. So what we must do now is we must compare, the final step is comparing the absorbance to a calibration curve. A calibration curve. And what a calibration curve is, everyone, is where you get a graph, right? So we get solutions that we already know the concentration of, and we find its absorbance. So before putting our actual iron thiocyanate sample, we would have ran multiple iron thiocyanate samples which we knew the concentration of, and we'd find the absorbance. So it looks like something like this. So this is our graph. We would have absorbance on the y-axis, concentration of iron thiocyanate on the x-axis. Is everyone with me? Right? And we'd pass it through colorimetry and would say, okay, a sample of iron thiocyanate with 0 concentration, aka pure water, would have 0 absorbance. Then we could measure the absorbance of a concentration of 1 mole per liter, and we might get this value. 2 moles per liter, get this value. 3 moles per liter, we get this value. And what we can do now is we can plot a line of best fit, and now we have our gradient. Do you all agree? And now if I know that my absorbance is 1.52, I can look at that calibration curve. I can find 1.52 and find the corresponding concentration. So that is how you use colorimetry. So to give you all a high level overview, what we do is we pass our sample through the colorimeter, we get an absorbance value, and we compare it to a calibration curve, right? Which is a curve where we've already run standard solutions, which we know the concentration of, and we measure their absorbance. And we plot the absorbance on the calibration curve to get the concentration of iron thiocyanate. Does that make sense? I know it's a lot of information because you're going to learn all of this again in module 8, but it does come back in mod 5. So you need to know the basics of this process, right? And this would include in exam questions. You could be asked to explain colorimetry. You could be asked this formula here. You could be asked the Beer-Lambert equation, which is much higher yield. Okay. And finally, you could be given an absorbance and asked to plot it on a known calibration curve that they give to you. Okay. Does that make sense to all of us? Do we have any questions so far?
Yeah. Would the color of the ions matter because they're yellow? So would that affect the absorbance of the iron thiocyanate ions?
Very good question. Since we're working with one solution that since it's an equilibrium, it's going to have some iron thiocyanate, it's going to have some iron 3 ions. You are right. The iron 3 ions will contribute and absorb some wavelengths of light. But for year 12, I think don't worry about that interference. That's possibly why we use blue light specifically rather than green, which is complementary to the red. But for year 12, don't worry about the interference with different colors. But very good point of thought. It definitely would. It's just it would have been accounted for based on this methodology up here. Good. Very good question. Any other questions at all?
Yeah, what's the units for absorption?
Very good. So it's absorbance. So where do we have it? We should have it somewhere here. Okay, I'll write it for us. Oh, there. Absorbance rather than absorption. And it's unitless. That's why we haven't mentioned anything. So very good question as well. Absorbance is unitless. Good. Any other questions at all? Okay, very good. I just want to preface this. Beer-Lambert equation is not just for colorimetry. It's a universal equation that you can apply to any form of spectrophotometry. All forms of spectrophotometry will be looking at measuring absorbance and we'll plot it against a calibration curve to determine concentration. So it's all the same principle. Okay. So you'll see this in AES, you do the exact same thing. You'll see it in UV vis spectrophotometry, we do the exact same thing. And so it's a very recurring equation. Good. So just coming back to this, hopefully you now understand we are going to use spectrophotometry to determine the equilibrium concentration of iron thiocyanate. Does that make sense to us all? And from there, using your Rice table, you can thus determine the K value. Now, you do not need to memorize the method for this, but you should have at least read the method and become familiar with it. In the HSC, they will never ever ask you to memorize and regurgitate a method in your exams, so don't worry about that at all. What you should know, though, is the general principles of a good scientific method. So this is a method for this experiment. You don't need to memorize it again, but can you all look at this and tell me, what are the 3 things you want to have in any scientific method you write? Because this is important for your depth studies. All of you will be doing one depth study. Part of it will be submitting a method, and you'll be scrutinized for every single step that you write there. And it's usually, 30% of your internal mark. So what determines a good scientific method? Look at this and tell me. So we'll start with Tanisha. What's one important thing?
You always have to use verbs.
Good. And instructive verbs, right? So you always want to start with instructive verbs. What else do we need for a good method?
Correct equipment.
Good. So we've got volumetric pipette, and you learn about all of that. And you want to know what a cuvette is. See, although you don't need to memorize methods, you need to be familiar with the equipment used. Anyone understand what a cuvette is? The cuvette is just this cube-shaped apparatus which holds the solution in the colorimeter. That's all the cuvette is. Typically, it's about 1 centimeter wide. That's what a cuvette is. Okay, so that's all you need to know. Did you all Google search colorimeter? Did you see the machines? Just so you understand what it looks like. When you do it at school, pay full attention in class, and then you will not have to ever worry about colorimeters because you would see it, you would understand it. Yeah, so good. What's the last thing I'm looking for?
Exact value.
Quantities. Good. Quantities is the last thing. Verbs, equipment, quantities. If you have those 3 things, no matter what you write, as long as you generally know the gist, you'll get full marks, right? As long as you don't say, 3 liters of iron thiocyanate, you have some reasonable amounts, you have some reasonable equipment, you'll get all the marks. Good job. Any questions at all? Okay, and I don't think I gave us a break for this lesson. I'm sorry, there's a lot to go through, but you're all doing really well, because I think after this, what are we on? Look at that. But we're pretty much on the last inquiry question already for Year 12, Module 5. So you're doing really well. Good job. Okay. I think for this lesson, we might end it there. Do we have any questions at all in general from this lesson? Any questions at all?
Yeah, for the Rice table.
Yeah.
You know how you had the initial change and the equilibrium?
Yep.
So can you do it without converting it to concentration and just do it like with the raw moles and then convert to concentration after?
Can you do it with raw moles and convert it to concentration after? thinking about it, you technically should be able to. Yeah, you should. You should. As long as, Mithilesh, your equilibrium, you eventually find equilibrium concentrations, you'll be right. But I would encourage you not to do that, because then you're heavily working with moles and you can make silly mistakes. I would say from the start, convert everything to concentrations. As a rule of thumb for me, in my rice table, I only have concentrations. Because the second you start mixing number of moles and concentrations, you start mixing things up and making mistakes. So I'd encourage, just so you don't make any silly mistakes at all, remember for the rice table, you only want to input concentrations. Good question. But you're right, technically you can, as long as the volume doesn't change and you divide it at the end to get concentration. Any other questions at all? Okay, I'm gonna ask two people what they learned today. So we'll start with Gerald. What's one important thing that you learned?
How to quantitatively analyze the equilibrium position by looking at colorimetry and the B-Lambert equation.
Good, very good. So colorimetry and the B-Lambert equation. So Pranav, what about you?
I learned, like, this isn't like really physics, but like I learned like the complementary colors and like, how you can use that to
Yeah, and it's applied in colorimetry, so that's why it's like it actually gets examined in chemistry. They will ask you about the color wheel as well, and they've done it in past trial questions as well. And last, Riasat, what's one thing you learned?
I learned that equilibrium constant, the importance of it is to find the equilibrium position. I did not know the complete importance of it before. Yeah.
Very good, good. I'm glad you all learned something. And make sure that you don't forget the concentration time graphs point, which concentrations change based on stoichiometric ratio. And if you've got concentrations at two different time points, Anj, what do you need to do?
Use the rice table.
Very good, right? So you've all mastered that. Good job. And next lesson, we'll start looking at solubility product in the last inquiry question of Mod 5 Year 12. Good job, everyone. I'll see you all next week. Have a good week.
Thanks, Prithvi.
Thank you.
Thank you.
Thanks.
Okay.
Thanks.